Hello? Okay. Thank you. Okay, so let's have a quick recap. So what did we do yesterday, sorry. So yesterday we proved that the expectation of this 1 plus z mn plus mn square. Okay. And then we show that this is bounded by 1 over eta square. Now we only do it for the second moment, but actually if you compute the any piece moment, it should also give you the correct order here if you do it carefully. And how did we do that? We use the Cume expansion. Plus some resolvent identity. Resolvent identity. Okay. And we show that n square. This is bounded by mn and eta times the first moment and plus some mn z plus 2mn divided by n eta square. This is what we proved last time. Okay, and then we observe that if we know that mn minus mnc can be bounded by some error, say epsilon, then this relation tells us that actually this guy will be bounded by a 1 plus epsilon square divided by n square and eta square. Right, because M is concentrated around MSC, which is bounded. This is bounded and it's epsilon, so just plug in and we get this one. Okay. And so this means that when eta is of order 1, this is quite trivial, right? When eta is of order 1, we know that the resolvent, the operator norm of the resolvent is bounded by 1 over n eta, or 1 over eta, which is of constant order. So this means that at the global scale, eta is order 1. G is a constant matrix. Each entry of G is constant order. And you just plug in. So epsilon is constant, right? So you will get 1 over eta immediately. So this means that on the global scale, you will get this one quite cheap. Sorry, 1 over n. Okay. And then we can do some recursion like this. So we start from eta, which is order 1, right? And we consider some level which is slightly below 1. Say n to the minus delta, and delta is a very small number. Okay? And by monotonity, we can show that on this line, we know that everything is bounded, right? So G is very close to the constant. Okay? So on this line, everything is bounded. So you can use some monotonity to prove that on this line, everything is not bounded, but so here, G is bounded by something, it's not bounded, but it's bounded by something n to the minus delta, n to the power of delta. Because on this line, everything is perfect, and you can estimate difference between them, and then show that difference is bounded by n to the 1 over n eta, it's n to the delta, right? So you can have some primary bound like this, and then you plug in. So you assume that your eta is n to the delta, and you plug in. You get some 1 plus n to the power of delta squared divided by n eta, right? You gain something, right? And then you do it again until you reach the fixed point, which is epsilon. So the fixed point, if you run the iteration, the fixed point would be epsilon is of size 1 over n eta. Okay. And once you know this level, and you can continue. You lower your level of eta to n to the minus 2 delta, right? And because you know that everything here is concentrated around constant order. And you can do it further and further until you reach the line 1/n, which is where you are really interested. So that's the basic idea of the proof. Yes?
So in your example, n stays for
M, yes. So maybe oh, sorry. Yes, this is exactly this guy. And sorry, I always, sometimes I mix with the capital and the small m, but you can guess what I mean, yeah. Yeah, so that's the idea. And you can see that actually this technology is quite effective when you consider a single resolvent of the matrix. Okay. However, if you consider for example, you can consider product of matrices, this terminology might not be very effective. I will show you. And you may ask why I cared about the product of resolvent, right? So the reason to care about the product of resolvent is sometimes you want to know. So maybe I give you some examples. So this is my G1. So G1 is a resolvent of the matrix evaluated at Z1. And Z1 is E1 plus I eta. And the eta is small, is the, okay. And my G2, H minus Z2 inverse. And this is my Z2. Okay. And by spectral decomposition, you know that for example, if I take the imaginary part of G, then this will become this one square eta by spectral decomposition because H is a self-adjoint. And here we have the eigenvectors. Uj, Uj star. Okay. So when your eta is quite small, say it's a typical space in CM, my eta is 1/n or something like this, or slightly above 1/n. Okay. So the main contribution from this term is coming from eigenvalues, which is quite close to E1, right? See, maybe the main contribution is from this guy. And lambda I is quite close to E1. Okay. And I can do the same thing for this guy. For the G2, it's the same thing. So the main contribution is coming from the eigenvalue, which is quite close to E2. This is EI, E1, and my lambda K, E2. Okay. And you may want to know the overlap between the eigenvectors here and eigenvectors here, right? Because if two eigenvalues, they are far from each other. If this E1 and E2 are far from each other, say E1 and E2 are far from their typical space in 1/n, then you can imagine that this particle is sort of independent of that particle, right? So this means that the quantity should be independent of this quantity. So you would like to see some decay between these two quantities in terms of the E1 minus E2, right? Okay. So how do you do that? You simply compute the G1 in G1, evaluate at E1, and you choose some arbitrary fixed matrix, say A. Sorry, I write this times A times the im G1 E2 plus I eta. Sorry, this is 2. Okay. So this is my G1 and this is my G2. And I can A star here. And I just look at the, say, k-case entry of this 2G resolvent. By spectral decomposition, I will get something like this. Sorry, I will get summing over J, sorry, I, J. So here I have lambda I minus E1 square plus X square times eta. Sorry. lambda J minus E2 square plus eta square, right? And we have the Uj, what should be that? Sorry, not the KK entry. I just started this resolving. I will get, yeah, probably the normalized trace. So normalize the trace of this guy. Okay, let's first write down carefully. So actually this is Uj star multiplied by A, and UK star, and multiplied by A star, right? And I will introduce a notation which I'm not sure if you like it. This is if I have the matrix, I have the bracket, which means I take the normalized trace. So this is the notation. I will use it for simplicity. Otherwise, I will write too many traces. Okay, so here I can take the normalized trace right here. And I take the trace here. And I divide by 1 over n. This is simply the, oh, no, this is a trace. Yeah. This is scalar. You can mention that. This is a scalar, actually. If you take the trace, this will become scalar, so you get 1 over n in front of it. And then this means that my normalized trace of this in G1 A in G2 A star, this will become 1 over n summing J, I and J. Okay, and this lambda I minus E square plus E square, and lambda J minus E2 square plus eta square. Okay, and on top I will have this Uj, Uj star A UK, and this is a scalar. I take the square norm, right? Because trivial is because the trivial properties, you can always remove it here, so you get square of them. Okay, and this guy, you know that your eta is chosen to be of 1 over n, something like that. So there's only one eigenvalue near here and one eigenvalue is near here. So you can get something like 1 over n, right? And this is the eta square. And here is eta square, and eta square got cancelled. And you will get this Uj A UK star square, right? Because your eta is chosen to be 1 over n, so typically speaking, there's only one eigenvalue that is close to this E, right? So you have this bigger than that, and then you will get Uj star A UK. This is eigenvector overlap on the observable A. Okay. So this should be bounded by n eta square times this guy. Is that clear? I might just do some linear algebra using spectral decomposition. And using that, you know, we just, our eta is not so tiny. Eta is 1 over n, so there must exist one eigenvalue that is close to this guy. If this is close to this guy, this means that lambda I minus E is less than eta, right? I can get bigger. Yeah, sort of. Yeah. So this is less than that. This is, if this is 0, then it's eta square. Okay. I will get 1 over eta square and multiply by the overlap, eigenvector overlap. So I can get something like that. So if I want to know the overlap here, this means I need to know this 2G resolvent. The resolvent of two. The estimate for the product of two resolvent. This one is evaluated at Z1. This one is evaluated at Z2. And we want to see that when Z1 and Z2 are far from each other, I want to see some decay in terms of Z1 minus Z2. Okay, so that's the picture. But you can see that, so we have some naive estimates, right? Because for 1G, we know that So the error is sort of like, so the 1G, for the single G, you know that the size of the resolvent is constant order, right? Oh, sorry. Should be A and A star. Yeah. This is important. Okay. Otherwise, if A is identity, this is sort of trivial, right? I mean, okay, so we have some naive estimate, and we have some naive bounds. So G is of constant order, right? So you have 2G, sort of like you take derivative of it, right? You can imagine that. So if we have 2G, the size of them is sort of, you can imagine that it should be of 1 over n eta, something like that. 1 over eta, sorry, right? And if we assuming that, okay, we use this crucial bound to say this is 1 over e. Sorry, am I correct? No. So what is that? So the G is like 1 plus 1 over n eta. This is error. So if I have 2G, I should get something like 1 over eta plus the order 1 over n eta squared. Something like that, right? So you have 1G is 1 plus 1 over n eta. You have 2G, and we know that the resolvent of G is always bounded by eta. So you mainly multiply by eta on both sides. So this is some naive estimate. Okay. And then you just plug in. What did you get? You will get something trivial. You will get NE squared times 1 over eta plus, I mean, this is smaller than that one, but eta is much bigger than 1 over n. Okay. And then you will get n eta. And then eta is 1 over n, right? So you get some constant order. And this is not effective, right? Because you know that the u is a unit vector, and the a is a bounded, you get nothing, right? Okay, so this means that we miss something. I mean, this means that this estimate is too rough. Okay. And let's see some example first, some special example. So what if I set identity G equals A equals 1? A equals identity. Of course, this is trivial. I just want to see the improvement on the right side when I set A equals identity. So what is my GZ1? GZ1, now A is identity, so I get GZ1, GZ2. And then we have the resolved identity, right, that I showed you yesterday. So GZ1, GZ2, this is equal to GZ1 minus GZ2 and divided by Z1 minus Z2, right, by resolving identity. And then you know that this is 1, this is order 1 plus some error, which is bounded 1 over eta, right, and divided by Z1 minus Z2. So this should be the order 1 divided by, Z1 minus Z2. And if we take the normalized trace, this should be of this size. So the fluctuation should be, of this size. And you can see that we indeed gain something from Z1 minus Z2, right? When Z1 minus Z2 is much bigger than eta. When Z1 minus Z2 is much bigger than 1 over n, then this estimate is much better than this estimate. Is that clear? Okay. And then you may say, okay, what if I said A does not equal to identity? If I consider arbitrary matrix, deterministic matrix? I mean, it's easy to guess. We should also observe some decay in terms of Z1 minus Z2, right? So identity should not be the special case. But you don't have any resolved identity. So that's the pity. So this sense becomes much more complicated if you choose a non-trivial matrix. Non-trivial matrix. Okay, so maybe the first task is to show, to figure out the deterministic approximation for this matrix G1A, G2, right? So we know that G1 is very close to a diagonal matrix, right? As we showed yesterday, we showed that this is very close to this guy. It's a dynamic matrix. And we know that G2 is very close to a diagonal matrix, like this. Okay. And you may guess what is G1A, G2. And naive guess is that, okay, maybe it looks like something like this. A. I just replace G1 by the diagonal approximation. And I just replace G2 by the diagonal approximation, right? And this is not correct, actually, because this approximation too weak. So it's not a strong approximation, actually. So what is the correct size? And this is not correct. Okay, so this correct size, the correct approximation for this G1A, G2, maybe I give a name. So the approximation is called G12A. This is the approximation to G1A, G2. And this matrix, for the single resolvent, the deterministic approximation, I call it M1. And here I call it M2. And the lemma says that the correct deterministic matrix should satisfy this equation. M12 minus M1, M2, sorry, the trace of M12, oh, maybe M1, M2, and this is defined by M1A, M2. So this is the correct equation for the 2G resolvent. So for the 1G, if you have only 1G, the approximation should be this. 1G approximation. You have 2G like this, and this good approximation to this matrix should be satisfy this equation. Actually, we can define an operator. This is called B12A. This is identity minus M1, sorry. Normalize the trace M1, M2. So this means that if you define the operator norm like this, if you define the operator like this, then this means that your M12 is simply this inverse operator of this guy. Right, I just define this is called a two-body stability operator. So this is the identity, so this is identity times this one. So it's, if we multiply, sorry, how do I say that? If I act on the operator A, then operator B, then I will get a B minus the trace norm of B multiplied by M1, M2. And this is indeed the inverse of M1, the inverse of this this operator act on this M1 A times M2, right? Okay. And this one, to start it, so remember that in a 1G problem, we know that if you get some self-consistent equation like this, if you want to solve it, you have to make sure that your z plus 2m should be bigger than 0, right? Should be away from 0, so that your solution is stable. And it's the same here. It's the same here. So if we want to inverse this operator, you have to make sure that the operator, the smallest eigenvalue of this operator is away from 0, right? Okay, so what is the smallest eigenvalue of this? Maybe let me first do some calculation here. So what did I get here? So I solve it, right? I take the average the trace everywhere on both sides. So I will get M12, right? and minus, so this is diagonal, so it's 1 minus M1, M2. And here, this is also diagonal, so it's just the trace of A times M1, M2. Right, I just take the trace on both sides and take the average. Okay? And then you can solve for M1 too, right? This is indeed M1, M2 divided by 1 minus M1, M2 multiplied by the trace of A. And you can plug in and you can solve for M1, 2. So actually M1, 2 is exactly given by, so M1A, M2 plus this guy, M1, M2 divided by 1 minus M1, M2 times average times the trace norm of A and times M1, M2. Yeah. So here you can see that if I set A is traceless, okay, if I set the trace of A is 0, okay, so this guy just vanished, right? You will exactly get what you get here. So M times A, right? And this one is so this one is a bad guy because this is constant order, right? And this is of size 1 over eta because you have the matrix times another matrix. So the size of this is, naive size of this is 1 over eta. And the naive size of this is just order 1. So you see that if you set your matrix to be traceless, then the deterministic approximation should be much smaller, right? Because this is the order 1 constant. It's the order 1 quantity plus something times a product of 2 matrices. And the product of 2 matrices will be much bigger than 1 matrix, right? When eta is very small. So this contributes to 1 over eta, and this only contributes to order 1. So this means that if you set your A to be traceless, you should observe that the deterministic approximation is much smaller. Which means that if you set your A to be traceless, you should improve the local law as well. Okay, so A is a bad direction. You can view that A is a bad direction with for this inverse operator, right? And you have to remove it. If you remove it, everything is fine. But the bad direction is just a constant, so the removing is not that painful, right? You just subtract, when you do something like this, you just subtract A minus the trace A, right? You will get some traceless thing right here. I denoted the A dot maybe. And so this is sufficient. It's sufficient for you to just put the traceless matrices here, right? Because this is identity. So UG, UK act on this identity is just one delta function, right? Delta JK. So this means that this can be written as UG star A, traceless A, UK, plus the delta JK minus plus trace A. Right, this is just that one. So it's sufficient for you to just look at traceless A. Right, otherwise, so. And as I said here, for traceless A, you should observe some improvement. And I will show you the result directly. So what is the improve? Yes? Z1. Yeah, my G1. Sorry, can you say it again? So my G1 is this H minus Z1 inverse. And M1 means that this is at MSC in value at Z1. Did that answer your question, or are you asking something different? You mean this equation? Yeah. This satisfied for a single G. Yeah, for 1G. So for 1G, it satisfies this equation. But if you have the product of them, you will satisfy a different equation. And for the different equation, for this 2G equation, 2G approximation, if you set A is traceless, you observe some improvements. than non-traceless A. And you expect that here, if you put traceless A, your error would be improved as well to see this Z1 minus Z2 something decay or something like that. Okay. Okay. I will show you the result. So first, if your matrix, if your deterministic matrix is traceless, and if it is not traceless, I would first say that the size of this deterministic approximation is of size 1 over eta. For general A, for arbitrary A, there's nothing you can improve. But if you put traceless A here, you can improve something. You gain additional eta. I mean, this is simply to solving this equation very carefully. If you solve very carefully, you don't have to do it very carefully. Actually, I already did that, right? If it's traceless A, right, this is order 1. But for more difficult, for more difficult model, you have to do something more. I mean, so usually to prove the local law, actually the main technical difficulty is not coming from the deterministic, the random part. Actually, it's coming from the deterministic part somehow. Because I mean, here I just show you Wigner, right? You could consider some more complicated model like A plus Wigner and A prime plus Wigner, and you want to show how these two systems correlated for different A and A prime, right? And for such model, I mean, you don't have semicircular, right? And here it's quite easy because I always have semicircular. So everything I can compute very precisely, right? If you have arbitrary A prime, it is not semicircular. Sometimes you cannot get the precise bound for the deterministic approximation effectively. So that's the main technical difficulty, I would say. But for a Wigner matrix, if we focus on the Wigner matrix, it's sort of okay. But the improvement in general. So if you have, for example, like this matrix, A plus W, even though you cannot write it in terms of semicircular distribution, but the improvement is the same. If you get a traceless A, you will improve it. So this is approximation for GA star. Okay, you have two traceless matrix here. So if you have one traceless operator, you will get a square root of eta improvement. If you get a two traceless operator, you will get square root of eta twice. So that's why you improve it from 1 over eta to order 1 in this case. And for the local law, okay, if for general A, no traceless, for general A, this is for general A, this is for traceless A. For general A, the error term is G1A, G2A, this is star. This is A. So the error is 1 over eta multiplied by another 1 over eta. This sort of makes sense because if you have only one G, you have 1 over eta, right? Actually, you can use the same technology that I introduced yesterday to prove this without too much difficulty. So you have 1G, you got the fluctuations 1 over eta and eta. You got 2G, you just bound another G by the operator norm 1 over eta, you will get the same thing. So I mean, to prove this is not very, very hard. It's just a repeat yesterday's proof. And for traceless A, you get some improvement. G1, G2A minus M12A. So this guy is also small. It's order 1. This guy is 1 over eta. Okay. And you can show that actually this is bounded by 1 over eta. So here you gain eta. because you include two traceless matrices. So the determinant guy is improved by eta, and the arrow, the fluctuation term, is also improved by 1 over eta. It's also improved by eta. If I have this, then I can show what I want right here. You see that where am I? Yes, here. I see this overlap is bounded by n eta squared times this normalized trace, right? Now before we used 1 over eta, we say we didn't get anything meaningful. Now we replace it by the improvement. Now there's no 1 over eta here, right? So the overlap is bounded by n eta squared times this guy, and this guy is order constant. This is what we assume here, right? It's order constant. And you set eta is 1 over n, and here you will get 1 over n. This is 1 over n. So this means that your UJ A is traceless, of course. A traceless UK. This guy is bounded by 1 over square of n. So that's sort of orthogonal, right? Is that clear? So you have the UG and the UK, they are K and J are different from each other, right? And your A is a traceless operator, right? You will get that actual overlap is bounded by 1 over square of n, so they are sort of orthogonal to each other. So they are sort of, So this implies that UJ A, just put back the trace part. UJ A UK. This guy minus delta JK A, trace of A. This one is bounded by 1 over square of n. So that's the conclusion. If you have proved this improved local law for 2G and with its traceless observations, with its traceless A matrices.
So what does it say about UG and
UG and UK?
Yeah.
They are just eigenvectors. Sorry, is there a question?
I want to translate that into words.
Translate that to words. So this means that should I see that? So this means that for any observable A, maybe the easy application is to choose A as a finite rank. Maybe I choose A like this, right? And what does this mean? This means that my UJ my UG1 times UK1 if it's finite rank, this means that, or maybe I just choose something like this. This is trivial. This will go back to this. Maybe I choose some. A is a rank 1 operator. See this. A is a rank 1 operator. Okay, and this will become UJ I mean, if you choose j equals k, okay, this will become uj, uj star act on this v. This will become, so normal matrix of this is 1 over n. 1 over n delta ij plus something like that. Am I correct? So this is a unit vector. I just plug in. So this is uj square. See? I mean, I'm not very familiar with I'm very bad at physics, but I saw that it's called the quantum unique ergosity. But I cannot recover it now, so it's called quantum ergodic, unique ergosity. The QUE. It's related to a dynamic system. I don't know how to interpret it, but this is a direct result of this guy, I think. Maybe you are better than this. Maybe you can. Yeah, I don't know. Physics, I'm very bad at physics. But there is some physical application of that by using the overlap. Yeah. Sorry? For all A, for all traces A. And this is true for all general A. This is true for all traces A. If you have traces A, you will observe some improvement. And this improvement will give you some non-trivial estimate here. Otherwise, you will get order 1, so this is not very interesting. Yeah. I don't know how to put. Anyway, and you can do something finer. Actually, you know that the fluctuations of whatever square fin. Actually, you can also, consider the fluctuation. You will get some Gaussian, blah blah blah. Yeah. Anyway, so I hope that I convince you that for traces A, this local law is sort of useful. Okay. And I want to say that if you want to use the technology that I introduced yesterday, you cannot prove this. You cannot prove this. You can try, but it's not effective. So that motivates us to. This motivates to introduce some powerful a new method. Probably there's a way that you can still use yesterday's technique to prove it. But anyway, so today I will introduce a new method that can be adapted to study this to prove this improved local law. And I would say that even though this method is new, but it's highly motivated from yesterday's idea. So you know some information from larger eta, and you let eta go slower and slower. Okay, lower and lower. Okay. Do that. Oops. So this is called some flow method. So what does the flow mean? This means that I want to add a dynamic to the system. So even though I start with Wigner, right? I want to start a Wigner, but I want to add time to this Wigner to make things better. So like Dyson-Browne motion. So I start from Wigner, right? So my H0 is still Wigner that I want to start it. And I let the matrix to run the Oldenburg process. So this means that entry-wise, the matrix entries follow the Oldenburg process. So it's the equilibrium measure will become the GUE or GUE, the Gaussian matrix. And I start from Wigner, okay? And then I can use Ito formula, the Ito formula, to derive the dynamics for G. Right, because G is a resolvent of H. Now we know the dynamic for H precisely. I can derive the resolvent. Okay, let's do it carefully. Okay, so I will get, So first I will get the partial G, the summing over A less than B. Remember that my matrix is self-adjoint, right? Only half of them are random variables. And I have the partial G, partial HAB, right? And multiply by DHAB. And I also have 1/2 summing over A less than B, summing C less than D. And a partial square G, partial HAB, HCD, right? And DHAB, DHCD. Right. Now this is yes, and then you just plug in. Here you will get A less than B, and here you will get minus G delta AB. You have two terms because it's self-adjoint. You have AB plus BA G, right? And you multiply it by this guy. So it's negative 1/2 HAB dt. And they also have the drift term, the martingale term, the diffusion term. Okay, you will get minus, and you will get plus. Okay, and this is minus AB G delta AB multiplied by whatever square root dBAB. And for this term, it's a bit more complicated. I apologize, but it's computable. So you have the G delta AB plus delta BA G and delta CD plus delta DC G. So this is the first guy, and you have twice of them actually. This corresponding to this guy. And this one, the quadratic variation, you will only get 1/n dt. Right. Hope I didn't make any mistake. And then delta. As is a delta is a sorry. Yeah, A less than B.
The last one.
Last one.
B equal to C.
Oh, yeah, that's correct. Sorry. We have the delta function because of this martingale. And so actually it's this delta AB. So actually there's no this one. There's no, so it's like delta AC, delta BD. So just remove this. So you have CD, AB, BC as well. This is one. Okay. I hope it's correct now. Okay. And then you have a and if you compute it here, you will get this is 1/2. You put H inside, you will get GHG. Because here I only summing over A less than B, right? And here I have two of them. Actually, I can remove one of them and bring back this the full summation, right? So I will get and you also multiply by HAB, right? And you sum of them, you will get GHG here. This is the first term, dt. Do something similar here. I will get minus 1 over square root of n and G dB G, right? This guy and this guy. And here I will have, this is a bit complicated. So this one, this 2, I bring back this full AB. And here I have two choices, right? Either I have this G delta AB, G delta AB, G. Or I have G delta AB, G delta BA, G. They contribute to different terms, right? This one will give you terms like G, GAA. And you summing over A, you will get G, normalize the G. Because you have one in here, and you will have the G square. This one will give you, oh, sorry, this is not correct. Oh, this is BA, BA. So this one will actually give you 1 over n G cube, right? And this one, will actually, here you get GBB, right? GBB, and you normalize by 1 over n here. So you will get a normalized trace. And here you have G square, so you have G square. So it's just a linear algebra, nothing, if you play with a little bit, you can tell that. And you have 4 terms. And, sorry, you have 2 of this, and this 2 will cancel with this guy, I think. So you will get this one, G square plus 1 over n G cube. And this is again dt. And here I can use the resolving identity here. So Hj equals Zg plus 1, right? Yeah, maybe I write it more carefully. Okay. So Gh equals Zg minus 1. Am I correct? Plus 1, sorry. H minus Z, yes. So this guy will become 1/2 times Zg plus 1/2 G. Okay, so now let's take a bracket on both sides. I can do that, right? Take bracket on both sides. Take bracket on both sides. And here we'll get bracket, and here we'll get bracket, okay? And here I also get bracket. Let's see here, bracket. Then I will get, to sum up, I will get D bracket G. So this is the normalized trace of G. should equal to, the first one is z over 2 bracket g plus 1/2 g. Oh, sorry, I forgot. This is square. Square, right? Sorry. Square. This is 1, this is 1. And I collect this guy here. So it's plus g squared plus 1/n g cubed dt minus the diffusion term. So it's a g dbg. Okay. And you see this one is not harmless, right? It's a linear term, right? Maybe I just put it in front. So this is 1/2 g. Okay, dt plus this is 1 zg squared. Okay. Huh? Yes. So this guy is not that terrifying because it's linear, right? But this guy is a bit annoyed, right? So what's that? This is 1/2 z plus g, right, times the g squared. Okay. So you can view this is of size order 1, right? This is more or less the 0 over 2 plus the MSE, so order 1. And this guy we can use we can bound it by, so this one can be bounded by the g absolute value, right? We can use the result identity to bound it by mn divided by eta. And when eta is small, this one is pretty large. This is too bad, right? And this guy, this is not that bad, but it's better than this one. Why? Because you have, you can use this g cubed. You can bound 1g by the operator norm. And then again, use this trick. So this one can be bounded by 1 over eta times the mm divided by eta. So even eta is much bigger than 1 over n, so this one is smaller than this one. You can see. So this one is subleading. This one is the leading guy, and this is the subleading guy. And sorry, this is the subleader. This is the subleading guy. Then how do we do that, right? It seems like we're stuck. So the idea is that we fix z, right? We fix z. As I told, I want my eta to change with t as well, because I get from the picture, right? If I go down, I can use some information from here, right? So I want to change my z as well. So how I want to choose a smart way to choose my z. So I just introduce a dot. So my zt, the argument of z is also depending on something. Okay. If I choose things like this, so if I choose a new t, so my gt is ht minus zt inverse. I can do the same thing for ht, right? But I got additional term for the zt. So I do the same thing. I got the additional term, which is coming from taking the derivative with respect to z. So I will get g squared multiplied by z dot t, right? Now if I change the argument, okay? And I want this z dot to q with the leading term here. So this is order constant. I don't like it. I want to gain something from here. So how do I do that? I just choose my zt to be negative MSE plus minus, negative z over 2 minus MSE. Right. If I do that, I will get something like this. I will get my derivative gt, right? So remember that my gt now is changing. Everything is changing. The matrix is changing. This is randomly changing. This is deterministic changing. Okay. I will get 1/2 gt. It's the same term here. But here, if I choose zt like that, this guy will cancel with this guy. And the remaining term is just this g minus MSC times this G square, right? Because this one plus this one, you will get a G minus MSC times this, and I got additional term, the same term as I said. And this is the drift term, and then we have the martingale term. This is, what's the martingale term? I lost my martingale term. 1 over square of n, G, D, B, G. Okay. So, yes. Outside? DT. This guy, we know that is bounded by 1 over eta, right? And this guy is 1 over eta. And this is 1 over eta. 1 over eta. So now they are, I'm removing the first leading term, right? And I got these two subleading terms. Okay, this helps a lot in our analysis. And of course, I mean, I want to know the difference between this guy, right? I want to know the difference between this guy. So I also have to subtract MT here. If you don't change Z, if your Z is fixed, it does not change with T, then you just minus MSC directly. You don't need to change anything. But now your MSC is also changing, right? Your MSC is changing with time. So you also have to take derivative of this one, right? If you take derivative of this one, you get F prime SC ZT times the ZT dot, right? So what is my ZT dot? My ZT dot is minus Z over 2 minus MSC, right? And what is my MSC prime? So 1 plus Z MSC plus MSC square is 0, right? I take prime, I take derivative, so I get MSC plus Z plus 2M MSC prime equals 0. I think I'm correct. Okay? So my MSC prime, this is simply the negative MSC divided by Z plus 2M SC. Plug in, right? So I will get minus MSC. This is 2 times Z over 2 plus MSC. I have minus that, and I multiply by this one. This got cancelled, and the plus, so I will get MSC divided by 2. Right. And this is perfect because MSC divided by 2 perfectly can match with this guy, right? So I just remove it, dGT minus MSC ZT. And here I will get MSC ZT. Okay. So I just introduced a new variable, so maybe say xt. So xt is defined to be the difference between GT and MSC. So average the trace of GT minus MSC ZT. So they simplify to derivative. Then the dynamics for xt, we have two terms. The first one is this. I use this maybe epsilon 1 x, epsilon 1 xt dt. And it's a martingale term. So maybe this is a drift term. This is a martingale term. Yes. So the drift term. So the drift term is given by this guy, G, so it's simply xt. So this guy is xt. It's bounded by xt times the IMPA divided by eta. This is bounded by this guy. Oh, let's do it. Sorry. So dxt, I have two terms. It's d1 dt. It's the drift term and the martingale term. And the drift term can be bounded by 1/2 plus MSC, the IMMC divided by eta times xt. Sorry, maybe I should take X value. This is simply because this guy can be bounded by IMM and divided by eta, right? And this one is even smaller than this guy, so IMM divided by eta. I think I'm correct. So this 1/2 is coming from here, and this guy is coming from here. IMM, because they always share the same g minus z1, but I still have this term. This term is bad. Can we just let this term go? I mean, at this moment, I don't know how to handle this term, but that means this term should be doable. It's even smaller. Let's just ignore this term for this moment. I don't know why you got this term, but this term should be okay somehow. But let's first forget this term. Just ignore it for simplicity. Just ignore it for simplicity. Okay. Then if I ignore this term, actually, I will get this gt minus MSC as the common factor here, right? So I just got this xt, and this one is 1/2, and this one I can bound it by IMM and divided by eta here. Okay. So this is my drift term. And this is quite good because here we can remember that we have the ground wire inequality for, say, for the deterministic matrix. If you have something like the derivative of ut is bounded by ATUT plus BT, say, right? Then you can show that actually your UT can be bounded using the initial condition, right? So it's like simply 0t at ds u0 plus, what is that, exponential integral, and the integral from 0 to t exponential st ar dr multiplied by bt ds. Right, so this is the ground wire inequality. You have a derivative of some function. You can bound it by itself, multiply by something. Right? You can bound this ut by using its initial condition plus some additional term. This is exactly what we do here, right? We have this. We take derivative of this guy, and we have this on the right. And we just first ignore this as a moment. I mean, we have additional technique to do with this one. Okay, then we'll get something like that. And this one, this is exactly, so this is your AT now. So we have to use a sort of it's called the stochastic version of the Galois inequality. Sorry. Okay. Oh, by the way, I haven't shown you that eta is indeed decreasing with respect to time, right? This is a key point. When involving t, right, we want eta to decrease in time. I haven't shown that actually. It's quite easy to see because my zt is this guy, right? This is my zt, right? I just take imaginary part, so minus the imaginary part of MSC. Remember that in the bulk, the IMPA is always positive. So this one is always of order 1. This is a positive, right? So this is always order 1 constant for all the time. So this means that d eta over dt, this more or less is negative, and you can view it as negative 1. So inside the bulk, I should draw the picture. So inside the bulk, now if you start from eta is order 1, inside the bulk, negative 2 to 2, so it's decreasing very fast. But if you are near the 2, actually it's decreasing slower and slower, something like that. So actually, in the bulk, the proof is simpler. For the edge, is more complicated because the eta does not decay that effectively. Okay, but in today's talk, we will only focus on the bulk, so it's totally fine. Okay, so then what is my xt? The stochastic Galois inequality will tell us that this is bounded by p0t of x0 plus the integral of t p s t d martingale term. And this is my pst is defined to be the exponential st, the drift term. I mean, there's nothing fancy. I just replace this. So now this is my AI, this is my AT, right? And my BT is simply this martingale term. This is my BT, right? And simply I just write down this integral in a stochastic way. So this is my P0t act on x0, right? And this is, I just write it in a different way. And now this P0, and this guy is a propagator, but it's just scalar, so it's okay. Okay, so let's compute the drift term first. So that my drift term is bounded by 1/2 plus the IMN, right? And now I need to take integral with respect to r. Sorry, zr. Okay. So what should I do? Okay, I've got something. I've got mm divided by eta. Am I correct here? Yes. I want to compute this guy. How did I do that? Remember that my d over dt, this is equal to negative eta t over 2 plus minus the mm, right? And I can divide by eta t on both sides. right? This means that this d log eta t. This is just the imaginary part. So it's simply the imaginary part this is MSC. MSC zt divided by eta t minus 1/2. Okay, minus. This guy is exactly this one. You see that? So this is exactly negative the derivative of this log eta t, and your is from s. Sorry, st. So this is simply the negative log eta t divided by log eta t divided by eta s. And this is very important. And from this, we can show that my PST here, this is bounded by e to the negative log eta t over eta s. So this is bounded by eta s divided by eta t. Okay. So just the upper bound for this exponential function. Okay. And besides that, I also need to control these martingale terms, right? Where's my martingale term? I also control this term here, right? To do that, I have to introduce a stopping time. So that I can use the BDG inequality. So that's the idea. I have to introduce a stopping time. How did I do it? How did I do that? So sorry, I forgot to mention the flow part. So the claim is like that. So if if you start from z0, you're assuming that you have this g minus MSC is bounded by n to the c divided by n eta, maybe 2 over c. So this is assumption, assuming that starting from time 0, you know that. Then you can show that up to time t, and time t has to be small, because your eta is decreasing. You cannot let your time to be too much to cross the real part. So you have to choose some time that is, say, fixed time, t star. Okay, and up to this time, you want to show that g minus MSC, this is bounded by n to the c divided by eta. So on the upper level, you have n to the c over 2. Here, you're assuming that here it is still correct, but you're adding additional n to the c over 2. But the c is a very small number, so it's okay. You can do that. Okay, so this is my claim. How do we do that? We just introduce a stopping time. How should I stop? I just the stopping time is that stopping time is the if as bigger than 0, such that the g minus MSC, this is bigger than c divided by n eta. So if I reach this line, n to the c over eta, I stop. And I want to show that this stopping time is exactly t star. This is my goal. If I show that, this is automatically prove that, right? Okay, so how did I do that? Because now tau is a stopping time, so I can bound this martingale term by using the quadratic variation, right? Because the BDG inequality says that BDG inequality implies that up to the stopping time, this guy, this is my martingale term. Okay, up to the stopping time, this, sorry, t. So this one should be bounded by with very high probability because the piece moment is bounded by piece moment of that, right? So with high probability is bounded by the quadratic variation of this guy, of the martingale term. Sorry, the quadratic variation. ds. Then what is my quadratic variation? I mean, if you trust me, because I don't have much time, but if you trust me, my quadratic variation is bounded by this guy. So 1 over trace, 1 over n. Sorry, what's that? If you trust me, I would say, maybe I write it down because I still have some time. So what is this? My martingale term. So the martingale term is this one. Is this 1 over square of n g d b g, right? So dm. So it can be written as 1 over square of n summing over I and j, and this is the g square ij times the db ij, gi. Right, just write it out. So the quadratic variation, you can write it out. So actually, this is here you have 1 over n, and sorry, this should be something 3 over 2, because I have the normalized trace. So here is 3 over 2, so you have 3 here, and then you have the summing ij, g square ij, db ij. This is the quadratic variation between this guy. And the kl, g square kl, db kl. And these are independent. So the entries of this guy are independent. So you get delta function, right? So you will get summing over I and j, 1 over n cubed, summing over ij, and g square ij takes square and dt, right? And this one is bounded by 1 over n square, and normalize the, I mean, you just bound one g by 1 over eta and bound the other one by mg divided by eta. So this is bounded by mm divided by n square eta cube. Okay. So this guy. And by BDG inequality, we know that this is bounded by quadratic variation, and I have to take the square root. Sorry, I have to take the square root. Okay, so what's that? So I have the square root of this guy. I just plug in, I have emem. I mean, it's because we are in a bulk, so emem is just 1. You don't have to carry it. So it's the n square eta cube dt. Right, my dt is proportional to d eta, right? Remember that. So this is almost the d eta. And if you compute, you will get something like 1 over n eta t, something like that. Yeah, so this one you get 1 over, yeah, eta t. That's correct? So let's plug in here. So let's compute this term, okay? So let's compute this term. So actually, I should not bound this. Actually, I should bound this one, right? I should bound the supernorm of this guy up to the stopping time. So actually, I should bound this guy. Sorry, didn't prepare well. PST, DMS. I should bound the quadratic norm of this guy. And it's the same. If you trust me, I just, this one should be bounded by should 1/2 square root of that. So this guy by BDG is bounded by BDG. So the sup of this is bounded by BDG by the square root of the quadratic covariation, and this is, if you write it out, you will get integral eta, integral t, sorry, just the integral of t p s t square 1 over the quadratic here. I will get n square eta s cube ds. This guy. Okay. Just do the computation as here. Okay. And what is my PSD? My PSD is bounded by this, right? So my PSD is bounded by 0t, and this is square is eta square, eta t square, right? And times this, eta square ss cube, right? And this got cancelled. You will get, and you have the square root, and then you will get I will get some log n, right? You will get some log n divided by n eta t, something like that, right? So this one is to bound this guy. I still have to bound this guy, and this guy is sort of easy because you just use this one. So it's just the eta 0 divided by eta t, and bound. Remember that x0, I assume that it is satisfy this equation, right? x0. So x0 is satisfied this equation, so I will get n to the epsilon divided by 2 and eta 0. And this got cancelled. You will get n eta t, n to the epsilon divided by 2. Okay. So this implies that up to the stopping time, xt is bounded by n to the epsilon divided by 2 divided by n eta, and some log n term divided by n eta. All of them are smaller than this one, right? So my heating time is assuming that I reach this guy stop and never reach this guy. So that's the reason why you have this conclusion. So that's basically the idea. So because the time is limited, so I only show the so for 1G, but for 2G you can do the same thing. Just to estimate these propagators, you have to use the deterministic approximation estimate precisely, and you will capture this. And here I also cheat a little bit because I didn't treat this part pretty well, but this part can also be done. Actually, in the complex case, this term is not there. Yeah, so it only appears in the real case, actually. Yeah, so yeah, so thank you very much.